So the last topic I want to touch on is polymers. We've already talked about polymers in the context of our nucleophilic acyl substitution, where we created long polymers like nylon using that kind of reaction, forming amides and esters. Another major type of polymerization that occurs is radical polymerizations. And those typically start from alkenes, which are treated by some sort of radical initiator. And so many of the plastics around us are made via this type of radical polymerization. So if we look at a few examples, one example takes these monomer units of ethylene. Remember, monomer units are the individual units, and when you put hundreds or thousands of them together, you get a polymerization. And so when we make the polymer of ethylene, we get polyethylene, where our pi bonds break, we make new sigma bonds between the ends of these carbons. So what we get is we have this 2-carbon chain, then we have a new bond, we have our next 2-carbon chain, new bond, our next 2-carbon chain, and we have a new bond, and we keep that going. So we often use parentheses and the n to show that this is happening an unknown number of times, usually a very high number, hundreds, thousands, 10,000s of units. And so this molecule, polyethylene, is found in most, plastic bags. It's found in a lot of different places, diapers, things like that. When we use substituted ethylene molecules, we get a very similar pattern. The only difference is we often get this sort of head-to-tail molecule where the less substituted carbon from one molecule of, let's say in this case, vinyl chloride, binds to the more substituted carbon of another monomer. And so we'll look at why this happens in a little bit. What you end up getting is something like this, where, let's say, this is our first unit, we form our new bond, and that more substituted chloride is going to go to the less substituted carbon. We're going to repeat and repeat. So I'm only going to show 3 units, but there are really hundreds, thousands, etc. And this, again, we can use parentheses, show that there's a lot of these, and this is the polymer known as polyvinyl chloride, or PVC, which is found, again, in a variety of applications. Piping is the major one that I can think of. We see the same thing with styrene, so we're going to use the same sort of pattern. I'm not going to show each new bond this time, but we're going to have a phenyl group instead of a chlorine. It's going to operate the exact same way, and this is going to repeat and repeat and repeat, and this is going to be polystyrene or styrofoam. So this is the structure of styrofoam. I don't really need to explain what styrofoam is used in. You all have experiences with styrofoam. And then tetrafluoroethylene, this is going to operate the same way, only each carbon now is going to have multiple fluorines. So again, I'm only going to show 3 monomers, but each carbon here has 2 fluorines coming off of it. This is our tetrafluoroethylene polymer, and that tetrafluoroethylene is abbreviated as Teflon. As we discussed when we were talking about our CFCs, when we have these sort of polyfluorinated compounds, there are some concerns about what happens when these build up in the environment over time. So there are some concerns about things containing Teflon, like pans, dental floss, things like that. Again, this is an ongoing concern in the environmental community, the public health community, the chemical community. So in the next slide, we're going to look at the mechanism at how these radical polymerizations occur and why we get this specific head-to-tail pattern. So for this, we're going to look at the formation of polystyrene, otherwise known as styrofoam. And so this is the monomer unit. This is the single unit that's going to be incorporated into the polymer repeatedly to make our new polymer. And one thing that you want to keep in mind is the chemical properties of the polymer come from the differences in functional group. So the addition of chloride makes PVC have very different properties than polyethylene, which means that the piping has very different properties than the plastic bag. Styrofoam, we know, has unique properties compared to both. So in terms of the mechanism, this mechanism is going to operate the same way as every other mechanism we've seen for polymerization. Start with some sort of radical initiator. Like before, we're going to use peroxides as our starting radical initiator. And this is just to get radicals in the system. Once the radical chain is initiated, then it's going to self-perpetuate. And to make materials with strong properties, you're going to want materials that have thousands, tens of thousands of monomer units. Then, once we've created this, we're going to start propagating our radical. So, the first thing that's going to happen in terms of propagation is that our oxygen-containing radical is going to combine with our alkene. And remember, whenever we react a radical with an alkene, we're going to form the more stable radical. And so in this case, the more stable radical by far is going to be the one with the phenyl group. And in all of these cases, it's going to be the more substituted carbon. So here we have our phenyl. This is where our radical is going to exist. And now we've made a new bond where we've started. We've made a new carbon-oxygen bond. Now this is going to continue to propagate. So this RO polymer is going to find another unit of styrene and repeat the same exact reaction. Again, we want to form the most stable radical. And so this is where we start getting this repeating pattern that we've seen over and over. Because making this bond in this way keeps the radical on the carbon next to the phenyl where it can be delocalized via resonance. So this step is going to repeat many, many times. Finally, what's going to happen is we're going to see termination. And so one option for termination is going to be that two chains are going to find each other and they're going to bind to each other instead of finding a new alkene. And this is going to be more likely once all of the monomer, or at least very much of the monomer, is used up. So I'm going to take two identical chains here, and show how they can combine. So here we have two radicals. If these encounter each other, the radicals will rapidly combine to make a new carbon-carbon covalent bond. So I didn't have very much room, so I wanted to draw it without talking over it. The new bond being formed is right here. And so here I showed it just after two propagation steps. This actually is probably going to happen after hundreds or thousands of propagation steps. But again, how often that this sort of thing happens is also going to contribute to the properties of that particular polymer. There's a lot more to polymers. There's also additional mechanisms that can form polymers, acidic mechanisms, anionic polymerization. There's many relevant things about the structure of polymers, the stereochemistry, but we really don't have time to get into that. But if you're interested, chapter 28 in your book goes into detail about polymer chemistry. And if we had more time, we would talk about it some more. But I just wanted to give you an idea of how radical chemistry is really important to a lot of the synthesis of our most used polymers, like polyethylene or polypropylene.